Welcome to this short video in which I would like to give you a small insight into my diploma thesis titled Differentially Pumped Mass Spectrometry Setup for Gas Composition Analysis of Molecular Beams. I'm Johannes Filzmoser. I did my thesis at the Surface Science Group of the Institute of Applied Physics at TU Wien. My work could be categorized as method development, addressing well-known phenomena and problems in experimental methods with new approaches. In surface science, experiments are conducted in ultra-high vacuum chambers where pressures are kept in the order of 10 to the power of minus 10 millibar or lower. The total pressure in such a system can be quantified with the help of an ion gauge, where the residual gas molecules are first ionized and then measured as a current. Often not only is the total pressure of interest, but also the partial pressures of specific residual gas constituents. This can be achieved with mass spectrometry. The first measurement step is the same as in an ion gauge, ionization of the gas molecules. Then specific species can be selected in the mass analyzer, and finally the ion current is measured at the detector. In the ionization step, various factors strongly impact the final measurement result. For example, the efficiency of the ionization and the ion transfer to the mass analyzer may affect the overall sensitivity. Most commercial mass spectrometers use electron impact ionization as their ionization method. With this method, one effect is particularly important at low pressures: electron-stimulated desorption. Electrons impinging on surfaces may cause desorption in the form of neutrals or ions. If these ions are transferred to the mass analyzer and then to the detector, one gets additional counts leading to wrong pressure readings. Before this ends up being a lecture about mass spectrometry, I want to give you some context. In our group, we are developing a near ambient pressure microreactor to investigate single atom model catalysts at elevated pressure and temperature. The working gases from the reaction cell are transferred towards the ultra-high vacuum analysis section of the chamber in the form of a molecular beam. The goal is to analyze the gas composition quantitatively and time-resolved using mass spectrometry. Since very low amounts of the reaction products are expected, it is crucial to have the ability to measure low abundance gases. One could define a signal-to-background ratio between the gas species from the reaction cell and their respective abundances in the vacuum chamber. This signal-to-background ratio tells you how sensitive you are to signals from the reaction cell, and it must be maximized. Furthermore, electron-stimulated desorption may also be a limiting factor, and it must be minimized. In my thesis, a conceptual design of an ionizer is presented which increases the signal-to-background ratio by differentially pumping of the ionization volume. It has been developed based on a near-type ionizer, which uses a magnetic field to confine the ionizing electrons. The ionizer geometry, the charged particle optics, and the applied magnetic fields were optimized using the simulation platform COMSOL Multiphysics. In a thorough simulation study, I investigated and optimized the trajectories of the primary electrons used for the ionization and the trajectories of the ionized gas species. With that, even the light H2+ ions could be extracted to the mass analyzer with an efficiency of about 88%. Furthermore, I looked at scattered and secondary electrons, as these may cause electron-stimulated desorption, and I could achieve that less than 1% of these electrons hit the surface inside the ionizer. Since my thesis is close to keep the option of a patent open, I would like to briefly switch from the results of my thesis to what I could personally gain from this work. The process of these simulations is often such that you come up with an idea based on your physical intuition, you simulate it, and afterwards you think about whether the results make sense. This process helped me to apply and interconnect the knowledge that I gathered throughout my studies. What I also really enjoyed about this work is that I could have a deep insight into the working principle of a measurement device. Wanting to understand a system or a device and not only seeing it as a black box is quite essential when doing experiments. Finally, I would like to thank my group at TU Wien, where I'm also doing my PhD now. especially my supervisor Gareth Parkinson and my co-supervisors Jiří Pavelec and Adam Lagin. Thank you.